Start chapter 6, or in 6.1, we're going to start with discrete and continuous random variables. So you'll see some things that look kind of familiar here. So first of all, what is a random variable? It's a numerical value that describes the outcomes of some chance process. So some examples could be the number of heads when tossing two coins, the number of girls out of 3 children born, the time it takes to walk to the corner. We'll also talk about the difference between discrete and continuous. So these two would be discrete, they're countable. The time it takes to walk to a corner would be continuous because we could go out to the 100,000s to the second. So I couldn't measure that and be as precise as I wanted to be, so that would be continuous. So what is a probability distribution? So we've seen these before in our probability tables. It's the same as it was in the other chapters. It describes the possible outcomes and how likely they are. So for example, tossing the coin, our outcomes are heads, 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 tails, tails, heads, tails, tails. So my probability distribution would be that. So first of all, we define the random variable. So X would be the number of heads when tossing 2 coins. So my probability distribution like this, the possible outcomes, I could get 0 heads, I could get 1, or I could get 2. Those are my only possibilities when I toss it twice. The probability of getting no heads is this one, so that's 1 out of 4. The probability of getting exactly 1 head is these two, so that'd be 2/4 or 1/2. And the probability of getting 2 heads is right there. So again, what makes it a legitimate table? All the outcomes that are possible are listed and the probabilities add up to 1. So the individual probabilities are between 0 and 1 and they add up to 1 total. So again, discrete is countable. So it usually takes on a fixed set of values. It could be an infinite set. We'll talk about binomial and geometric distributions later in this chapter. So geometric could be how many times until you're successful, so maybe you're never successful. So often discrete are countable. So if I say the number of girls born, you can't have a partial girl born, so it's going to be 0, 1, 2, 3, how many siblings you have, your shoe size, the number of classes you're taking. Those are all discrete and countable with probably integers or whole numbers. So looking at a distribution, we're going to figure out how to find out the mean and standard deviation of one of these. So in roulette, there's something called a corner bet. So you put your chip on the intersection of 4 numbered squares. So if one of these numbers comes up and you bet $1, you get your dollar back plus 8 more. Otherwise, if you lose, the casino keeps the dollar. So X is the net gain. So again, we're always defining our random variables. The net gain from a single $1 bet. There's only 2 outcomes. You lose, which means you lose your dollar, or your net gain, you'll get $9, but you already gave them, you paid $1 and then you got 9 back, so you really only netted $8. So these are the 2 possible outcomes. You either lost $1 or you gained $8. And there's 38 numbers on the roulette wheel, so you're betting on 4 numbers. So 4 numbers out of the 38 would be considered a success, so the other 34 out of 38 would be you losing. So if you were to make this dollar bet over and over, because again, this is all about the long term, what would be the player's average gain? So there's something called, so the mean, so again, this is mu for mean, the mean of the random variable X. We might also see it look like this. This is called the expected value, and you'll see this on the next page. So I would simply end up adding this 34 times, so it'd be -1 plus -1 plus -1 34 times, and then plus 8 plus 8 plus 8 plus 8 all over 38. There's an easier way to do that. We would have added 34 -1s, and we would have added 4 8s, and we would have divided that by 38, and we would have ended up with a negative 0.05. So what does that mean? It means if we were to make many $1 corner bets, we would expect to lose $0.05 for every dollar bet. So in the long run, we would expect to lose 5 cents per bet. So that's, again, in other words, casino keeps an average of 5 cents for every dollar bet. Think about that. Think about how many people go through and play roulette. Every corner bet made, they're making 5 cents every time, and they're playing all the time. So that's how they make their money. So you lose an average of 5 cents per bet, but the casino gains 5 cents per bet. Okay, another example on languages. So imagine selecting a high school student at random. We're going to define the random variable x as the number of languages spoken by that student. The table below, sorry, this keeps blurring in and out. The table below gives the probability distribution of x based on a sample of students. So this table's already filled out. But again, if you have to verify that it's legitimate, there's 2 steps. Number 1 is each probability is between 0 and 1. And 2, the sum equals 1. So in other words, if I added 0.630 plus 0.295 plus 0.065 plus 0.008 plus 0.002, again, I always recommend showing your work. I know you can type this in the calculator, but write down that that's what you're doing. So the sum is 1, verified, and each probability is between 0 and 1. So it is a legitimate probability distribution. So if I wanted to make a histogram, this goes back to chapter 1. So I have my outcomes are and then my highest probability is 0.63, so I'm going to count by 0.10s. So I just have to go up at least to my highest. And so again, always label. If you don't label, that goes from an E to a P, a partially correct if you don't label. So number of languages spoken, and this is the probability. So I'm always labeling not just the numbers, but what the numbers stand for. So my first one is 0.63, so about right there. And then my second one is 0.295. And then 0.065. Then these are probably barely even legible. They're so small. So they're there, but they hardly have any height at all. Again, describe what you see. Don't forget your socks. So shape, distribution, and the biggest thing I see in rubrics for the AP exam is no context. So the distribution of languages spoken by a U.S. high school student is skewed right. Now there's no gaps in there, so I'm not even going to say there could be outliers, but I'm not going to worry about that unless there's a gap. So possible outliers, the center, your center that's so high, the middle 50% is still in block 1, so the median or center, so there's my center with median 1, and the range is my spread, and the range is 5 minus 1, the range is 4 languages. So again, describing a distribution is talking about SOC, shape, center, spread, any unusual features. So what is the probability that a randomly selected student speaks at least 3 languages? So again, I want us to get in the habit of writing. What's the probability? Again, X is a random variable. At least 3 means 3 or more. So that or equal to matters here. So 3 or more would simply be adding up these 3 boxes. So 0.065 plus 0.008 plus 0.002. Again, always show your work. So that would add up to 0.075. So about 7.5% of these randomly selected students speak at least 3 languages. More than 3 is not or equal to, so more than 3 would be adding just 4 and 5. So now we go down to 1%, speak more than 3 languages. So how do you calculate the mean, which is also called the expected value? I put this on the first page, so it could look like this: the mean of the random variable X, or the expected value. The expected value is the average. So all we have to do is take each individual amount in our X's, multiply it by its probability, and add them all together. And then how do we interpret it? It is the long run average. That's those many, many trials. It's the long run average of many repetitions of events. Whatever the event is. So it's the long run average. And here's a generic sentence for us to use. And we will just fill it in with context. So you'll fill it in with the context of whatever the problem is about. So if I were to repeat the random sampling process repeatedly, the mean number of blank would be about blank in the long run. So we'll fill in the blanks in context with a problem. So in the languages, we're going to calculate the mean of the random variable X in that previous problem. So the expected, so we had one language was the probability was 0.63, 2 languages was 0.295, 3 languages was 0.065, 4 languages was the 0.008, and 5 was 0.002. So my expected value is 1.457. So we calculated, don't forget if it asks you to interpret. So if I were to repeat, taking my sentence from above, if I were to repeat the random sampling process repeatedly, so this is not a creative writing class, it's just say it over and over again. If I were to repeat the random sampling process repeatedly, the mean number of languages, I ran out of room, of languages spoken by a U.S. high school student, again, don't just say languages spoken, because we're talking about high school students from the US, would be about 1.457 in the long run. So there is my sentence of interpreting what that means. So I just took this, I wrote this sentence, the mean number of, what was the context, the number of languages spoken by a high school student in the US, and what the mean was. Okay, so a lot of times I see rounding. Does the expected value have to be one of the possible values? Do I have to say 0, 1, 2, 3, 4, or 5? No. In fact, many students have done the AP exam incorrectly believe that it has to be one of the numbers. But remember, it's an average and doesn't need to be rounded to a whole number. So as long as it's an average, it can not make sense because somebody isn't going to speak 1.4 languages. They either speak it or they don't, but we can say an average and have that decimal number. Okay, so how do you calculate the variance and standard deviation? Are these on the formula sheet? Well, the standard deviation is, in the old formula sheet, they gave us the variance, but the variance is just the standard deviation squared. So this is what's on the formula sheet, and we did standard deviation before. It's the average distance from each individual to the mean. So we're going to subtract those, we're going to square it and multiply by the probability, and then take the square root of the whole thing. If I don't take the square root, then I have my variance, and we'll talk about that later on, why we need variances also. So again, how do we interpret it? It's the average distance the individual outcomes are from the mean. Okay, so use your calculator to calculate and interpret the standard deviation of x in the language examples. So again, I'm going to say the standard deviation of x is going to be the square root of, and now I'm going to take, so our first number was 1 language, and then we're going to subtract our mean, square it, and multiply by the probability, plus 2 languages spoken minus the mean, times its probability. And then continue. Now I could put a dot, 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 but there's not too many here, so these are the notes. I'm going to actually write it all out. Okay, so if I subtract each individual from the mean, square it, multiply by its probability, and then I'm going to add those all up, and I'm going to take the square root of the whole thing. So if I add those up, so this 0.45 is the variance. So when I take the square root of that, I get about 0.67. Again, context, these are languages. So interpreting that, I would say the average distance each number of languages spoken from the mean is about 0.67 languages. So are there any dangers to be aware when using the calculator to find the mean and standard deviation? Because the calculator can do it for us. You just have to show some work to get credit. So like I said, the first couple of terms is fine. If I had shown this and then said plus dot, 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 that would have been enough for the grader to know you knew what you were doing, even if you did it on the calculator quickly. And I'll show that later. Okay, so those were discrete. Then we have our continuous random variables. So these are when we can't actually count, when there's an infinite number. So how many numbers are between 0 and 1? There's an infinite number of numbers between 0 and 1. So the amount of time it takes to run a 100-meter hurdles race, again, it's continuous. They're going to measure it, but they could be so much more precise and have an infinite number of times versus the number of hurdles. If I said how many hurdles did they cleanly jump over, that would be countable and discrete. Somebody's age, again, you could say is continuous because I am now 1 second older than I was a second ago. So my age is constantly changing. The number of birthdays that I've had, that is countable and discrete. So is it possible to have a shoe size equal 8? Yes. Is it possible to have a foot length be 8 inches? Again, we can be a lot more precision with foot length. Again, I could go out how many number of decimal places I wanted to. So how many possible foot lengths are there? It's infinite. So a histogram with an infinite number of really skinny rectangles. So if I made up a histogram, it's going to look like our normal distribution, or it could be a skewed distribution, but it would look more like our curved density curves versus a rectangular histogram. So same way we've been finding probabilities under the area of the curve. So finding probabilities, we just calculate the area under the curve. For a continuous, hopefully we can turn it into a normal distribution. Now here is when the inequality or equal to doesn't matter. In a discrete, on that previous page, when I said at least 3 or more than 3, they were different. But here, it doesn't matter. So the boundary line adds no area. If I asked you for the area of a line, it doesn't exist. Then I talk about dividing by 1 by infinity. Okay, so weights of 3-year-old females. So the weights of 3-year-old females follow a normal distribution. So that goes back to chapter 2. It gives us the mean and the standard deviation. Randomly choose one 3-year-old female and call her weight X. So find the probability that a randomly selected girl weighs at least 30 pounds. So a couple things you can do to show your work. One is to draw it out. Show the mean as 30.7 and show the standard deviation of 3.6. So I just need to add 3.6 here once. So if I add 3.6 to that, I'm going to get 34.3. So I'm showing that that is one standard deviation. So I'm showing it's a normal distribution. I can even do this. It's a normal distribution with mean and standard deviation. The other thing I can do then is show where 30 is. So what are we finding? We're finding the area that's at least 30 pounds. So if this is 30, I'm finding the probability that she's at least 30 pounds. So again, it doesn't matter. So she's at least 30 pounds. She weighs 30 pounds or more. And if I do this on the calculator, again, you wouldn't write this on the AP exam because they don't care about this. They care about this. They care about this, showing direction. They care about the shading. These two things show the same thing. This shows a normal distribution with a mean and standard deviation and the area, or saying it's a normal distribution. And again, this shows which area you're shading. So then you could go on and do normal CDF and put in your lower bound, which is 30, put in your upper bound, which is a really big number, and then putting in your mean and your standard deviation. And we would get that that is about 0.575. So about 57.5%. Now you could have also found the z-score. So if you had done the z-score, you would have done 30 minus 30.7 divided by 3.6 and gotten a z-score of negative 0.19. And I expected it to be negative because 30 is to the left of the mean. So I also could have done what's the probability that z is greater than negative 0.19, and I would have gotten the same outcome, except I would have had 0 and 1 there. So if this would have been negative 19 was my lower bound, a really big upper bound, and 0 and 1, that would have been my normal CDF if I were doing the z-score. So negative 19 would have been my lower bound, a big number for my upper bound, mean 0, standard deviation of 1. So I showed work 3 different ways. You only have to choose one of those ways to show your work. So find the probability. So since I've already said it's a normal distribution with a mean of 30.7 and a standard deviation of 3.6, I can now just say this. What's the probability that our x is between 25 and 35? So again, if you drew a quick sketch, you know your 30.7 is in the middle, so 25 would be somewhere down here, 35 would be somewhere up here, and this is what you are finding. So I could do z-scores again, but I can just again do my normal CDF. And now my lower bound is 25, my upper bound is 35. Again, I'm just being extra cautious and labeling everything that I should have done up there too. Lower bound, upper bound, my mean is 30.7, and my standard deviation is 3.6, and that will end up giving me an answer of about 0.827, so about 2.7, there's a probability of 82.7% chance that I will get a 3-year-old that weighs in that range. Okay, now I want to know what the K is if the area is 0.8. So I'm looking for a value K where the area below it, so I know that this is 0.8. I know that this is 80%. So this is where I do my inverse normal. And I'll put in the area to the left. So 0.8 to the left. I'll put in my mean and my standard deviation and get 33.7. So this is saying there is an 80% chance a randomly selected girl, 3-year-old, weighs less than 33.7 pounds. And that's it for section 6.1.